Problem 127, chapter 5. This is a very good problem. It has everything in it. So we have a disk here, which is rotating without any sleep on the floor. We know the velocity of point O, the center of the disk, is 3 meters per second to the left. And acceleration of this point is 5 meters per second squared to the right. And also we have this slot on the disk, and there is a particle which is moving on this slot. And the velocity of this particle with respect to the disk, with respect to this slot, is 2 meters per second to the right. And acceleration of it, or change in the speed of it, is 7 meters per second squared to the left. So this velocity and acceleration, this u and u dot, is for someone who is sitting on the disk and looking to this particle. So if you sit on this disk and look at this particle, you are going to see the velocity of this particle is 2 meters per second to the right. And changing the speed of it, u dot of it, is going to be 7 meters per second squared to the left. Now the question is, what is the actual velocity and what is the actual acceleration of this particle? It's a very good problem. It deserves to spend like at least 15 to 20 minutes on this before seeing the solution. So please stop the video and try to solve it yourself. Try your best. Spend at least 20 minutes on this one. Then come back to this video and see the solution. So I'm going to assume you did that, and now we can solve it together. So first of all, I need to define these two coordinates. First one is sitting on the ground. I'm not going to show it, x and y direction, capital X and capital Y. And the other one is this coordinate, small x and small y, which is fixed to the disk. It is rotating with the disk. It is like what I said, if you are sitting on this disk, you are not going to understand that you are rotating. Let's say you don't know you are rotating. Then you can look at this particle and see how it moves. So that's this coordinate, x and y coordinate, which is fixed to the disk. Now I need to find, first of all, what is the acceleration and what is the angular velocity and angular acceleration of this frame, which means the angular velocity and angular acceleration of this disk, right? Because we are going to need that in those equations. Velocity of the center is given. It is 3 meters per second. And the disk is rotating without a sleep. If you remember, we said velocity of the center of the disk, when it's rotating without any sleep, it's going to be r times omega of the disk. Velocity of the center is given, and we know the radius of the disk, so we can find angular velocity of the disk. It is moving to the left, so angular velocity of the disk is going to be in counterclockwise direction. So angular velocity of the disk is velocity of the center divided by the radius of the disk. So it's going to be 3 meters per second divided by 0.3 meter. So it's going to be 10 radian per second. And what is the direction of it? It's going to be in counterclockwise direction, as I showed it here. And also, again, if you remember, for a rotating disk without any sleep, we had this equation. Acceleration of the center is going to be r times alpha. Acceleration is to the right, and because of that, angular acceleration is going to be in this direction, in clockwise direction. So angular acceleration is going to be AO divided by R, or 5 divided by 0.3, or 16.67 radian per second. squared, and just in parentheses, this is in clockwise. The other one was in counterclockwise. I showed them here too. So this is the angular velocity and angular acceleration of the disk, which means angular velocity and angular acceleration of the rotating frame. That's one thing. The other thing that we need to figure out is what is the relative velocity of this pin or this ball in the rotating frame in XY coordinate, and also what is the acceleration of it. So let's start with relative velocity. Relative velocity of this guy is given. It's going to be 2 meters per second to the right in the I direction. So V rail is just simply 2 times I meter per second. How about the acceleration of it? Acceleration of that particle in the rotating frame, A rail. It says, the problem says the change in the velocity U dot is to the left, and it is 7 meters per second squared. Is that the total acceleration of this pin in the rotating frame? No, it is not. Look at this pin, look at this ball. It is moving on this curve, right? So acceleration is gonna have 2 components, tangential part, U dot, and also the normal part. The problem is giving us only the tangential part of acceleration, but we are gonna have a normal acceleration toward the center, which is equal to velocity squared divided by R, right? So the relative acceleration of that particle in the rotating frame, in XY frame, is gonna be negative 7 meters per second squared in the I direction, and also U squared divided by 0.24 in negative J direction. So it's gonna be negative 2 squared divided by 0.24 in the J direction. So this is the relative acceleration. So after finding this, let me actually finish this. This is negative 7I, negative 16.67 J meter per second squared. So after finding this relative velocity and acceleration, now we can use the equations that we learned in this section to find the actual velocity and actual acceleration of this point. The actual velocity of this point is equal to velocity of the origin of the coordinate, VO, plus V rel, plus omega cross R. And R here, the location of the particle in the rotating coordinate, is OA. So it's going to be equal to velocity of O. Velocity of O is given. It is 3 meters per second in negative I direction. Relative velocity, we found it here. So it is 2I. Omega cross OA. Omega, we found it to be in counterclockwise direction, and the magnitude is 10, so it is 10 k hat. Cross product to OA. OA is 0.24 in J direction. Now we need to do this cross product. K cross J is negative I. So it's going to be negative 2.4 in the I direction. So altogether, it's going to be negative 3.4 in the I direction meter per second. So this is the actual velocity of A. And for acceleration of A is equal to acceleration of the origin of the moving coordinate, AO here, plus relative acceleration of A in the rotating frame, plus alpha cross R, plus omega cross R. R here is OA, so let me write it OA from the beginning. plus the Coriolis acceleration, 2 times omega plus cross v rel. So we can just plug in the numbers. Acceleration of O is 5 to the right, so 5I. The relative acceleration, we found it here, negative 7I, negative 16.67 J, plus alpha cross OA. Alpha is in clockwise direction, so it is negative, so it's going to be negative 16.67 in the K direction. Cross product to OA, OA is 0.24 in the J direction. Omega cross OA, if you remember, we said we can replace it with negative omega squared times OA. Omega is 10, so 10 squared, times OA, which is 0.24 in the J direction. There is no cross product here. Then plus 2 times omega, 2 times 10 in the K direction. That's my omega. And then cross product to V rel, and V rel is 2I. So if you do these cross products and add all of them together, acceleration of A is going to be equal to I hat negative 0.667 J hat meter per second squared. That's going to be the total acceleration, or the real acceleration of A.